Welcome to our deep dive into a paper all about Adam. Adam's an optimization algorithm, and this paper has had a huge impact on machine learning.
Oh, yeah. It's a game changer for sure. It helps train machine learning models so much faster, which has led to breakthroughs in all sorts of areas, from image recognition to natural language processing.
Exactly. So we're going to explore the benefits of Adam and how it improves on older optimization techniques like AdaGrad and RMSProp. But don't worry if you're not a machine learning expert, we'll explain everything.
Yeah, even if you only kind of get gradient descent, you should be able to follow along. And hopefully have some aha moments.
So first things first, what problem are we even trying to solve here?
Well, imagine like you're trying to find the lowest point in this vast landscape that's always changing. That's basically the challenge of optimizing what we call stochastic objective functions in machine learning. These functions tell us how well our model is performing. And so the goal is to find the best parameters, the lowest point, if you will. That'll make our model as accurate as possible.
So we're like navigating this tricky, always changing terrain. And we need a good guide to help us find our way.
Exactly. And that's where gradient descent comes in. And think of it like a compass that always points downhill. It uses something called mathematical gradients, basically like directions. They tell us which way to adjust our model's parameters so we can keep moving toward that lowest point.
Okay, so it's like we're taking these small steps downhill, guided by our trusty compass,
Oh,
until we get to the bottom.
yep.
But I've heard that traditional gradient descent can be a bit slow,
Mm.
especially with like huge data sets and complex models.
Yeah, that's right. It's like taking these tiny steps down a really gradual slope. You'll eventually get there, but it might take a while. That's where stochastic gradient descent comes in, or SGD. It basically takes bigger and bolder steps, trading off a bit of precision for speed.
So we're speeding things up.
Yeah.
But then we have AdaGrad and RMSProp, which are supposed to be even better than just basic SGD. Where do they fit into all this?
Yeah, so both AdaGrad and RMSProp were developed to make SGD better, each with their own strengths. AdaGrad is really good at handling sparse gradients. This is when like a lot of the gradient values are zero. It adapts the learning rate for each parameter based on how often it's updated. So like parameters that need to be adjusted more often get more attention.
So AdaGrad is giving a little extra help to the parameters that are lagging behind.
Exactly.
What about RMSProp?
RMSProp is great at dealing with non-stationary objectives. Remember that shifting landscape. RMSProp is good at adapting to the constant change. It's like having a compass that can reorient itself, even on shaky ground.
Does both of these algorithms have their own advantages? But the paper we're looking at today introduces Adam, which is supposed to combine the best of both worlds. It's like the ultimate optimization superhero, right?
Exactly. ADAM, which stands for Adaptive Moment Estimation, takes the best parts from both AdaGrad and RMSProp. It calculates individual learning rates for each parameter, just like AdaGrad, and it uses momentum to speed up the whole optimization process, similar to RMSProp.
Wait, momentum. Is that like the when a ball rolls down a hill and gains speed as it goes?
Yeah, that's a perfect analogy. In Atom, momentum helps us speed up how fast it takes to get to the best solution by looking at the history of past updates. So instead of just reacting to the current gradient, it uses information from past gradients to build up momentum and make faster progress towards that lowest point.
So it's using the momentum from previous steps to keep moving forward.
Yeah.
That makes sense. But I'm curious about the math behind this superhero algorithm. Can we like dive in a little bit without getting too lost in equations?
Yeah, definitely. So basically, Atom keeps track of two things, the first moment and the second moment of the gradients. The first moment is like the average of the gradients, gives us a general sense of direction. And the second moment is like the variance of the gradients, which tells us how spread out the gradients are.
Okay, so it's like keeping tabs on both the direction and the spread of our compass readings. But I read something about bias correction. What's that all about?
That's a great question. When we start calculating these moments, they're actually a bit biased because we start them off at zero.
Yeah.
So Adam uses this clever technique to deal with that bias, to get more accurate estimates, especially in those early steps of the optimization.
So it's like making sure our compass is calibrated before we go into the unknown. Seems like Adam is really thoughtful in its approach. Now, there's this other interesting concept, the signal-to-noise ratio, or SNR. What's that all about?
Ah, yeah. The SNR is like a way to tell how confident we are in our compass readings. A low SNR means that there's a lot of uncertainty, a lot of noise in the gradient estimates. And so Adam cleverly adjusts the step size based on this SNR. When the SNR is low, it takes smaller and more cautious steps.
So it's like Adam saying, hey, the terrain's a bit shaky here. Let's be careful not to take any drastic steps. It almost is a sense of self-preservation. But tell me, how does Adam actually perform in practice?
Well, that's where things get exciting. The paper describes all these experiments on lots of different machine learning models, and the results were very impressive. Let's start with something relatively simple: logistic regression.
Okay, so let's see how our superhero algorithm does in a more straightforward setting.
Right, so on the MNestic dataset, which is a classic benchmark for handwritten digit recognition, Adam did pretty similar to SGD with momentum. Both of them converged faster than AdaGrad.
So even with a simple task, Adam is already showing its speed and efficiency. But I'm guessing things get even more interesting when we start to use more complex models.
You're absolutely right. That's where we really see Adam shine. Let's take a look at what happens when we use it for multi-layer neural networks.
All right, let's crank up the complexity and see how Adam handles the challenge.
Now, these networks have what we call non-convex objective functions, which basically means our landscape is a lot more rugged, with lots of valleys and hills. It's like trying to find the lowest point in a mountain range, instead of just a single hill.
That sounds tricky. So how does Adam navigate this more treacherous terrain?
Well, in these challenging terrains, Adam always did better than other methods. In fact, it got a very impressive speedup compared to another algorithm called the Sum of Functions Optimizer, or SFO. And this was especially noticeable when the networks were trained using dropout, which is a technique that adds some noise to prevent overfitting.
Wow, so Adam can handle the complexity of these multi-layer networks.
Mhm.
And the randomness of dropout, too.
Yeah, exactly.
That's really impressive. But what about convolutional neural networks, or CNNs? Those are known for being especially tricky to optimize.
You're right, CNNs are really unique because of how they're structured and how the gradients are calculated. Interestingly, while both Adam and AdaGrad showed promise initially, Adam and SGD with momentum took the lead and converged much faster than AdaGrad.
So AdaGrad fell behind in the long run. That's surprising. What happened there?
It is surprising. The paper actually suggests a really interesting reason. It seems like in CNNs, the second moment estimate, which captures the variance of the gradients, becomes less important, and reducing the variance that gets introduced by using mini batches of data becomes more important.
Okay, hold on. Mini batches. Can you explain that a little more?
Sure. So when we train these large models, we don't usually use all the data at once. We split the data up into smaller chunks called mini batches. This makes training more efficient, but it also adds some randomness, because each mini batch is just a small sample of all the data.
Ah, I see. So it's like we're only seeing a little snapshot of the whole picture.
Exactly. And this randomness from the mini batches can actually affect the optimization process more than the variability of the gradients themselves.
So it's like the shakiness of our compass readings from using mini batches matters more than the inherent shakiness of the gradients themselves.
Precisely. And Adam, because it focuses on both the first and second moments, can handle both kinds of variance, which is probably why it does so well in these settings.
This really shows how adaptable and robust Adam is. But the paper also talks about something that seems like a small detail, but it turns out to be super important: bias correction. Why is that such a big deal?
Remember how we talked about Adam's moment estimates being a little biased because we initialized them at 0?
Yeah.
Well, bias correction basically makes sure these estimates are more accurate, especially at the beginning of the training process.
So it's like fine-tuning our compass. Before we head into the unknown, what happens if we don't do bias correction? Does it really make a big difference?
Well, the paper looks at this by basically turning Adam into a version of RMSProp with momentum and taking out bias correction. And the results were pretty interesting. Without bias correction, the algorithm became unstable, especially when the decay rate for the second moment, beta 2, was close to 1.
So those values of beta 2 close to 1, which are important for sparse gradients, make bias correction even more critical. Seems like a small thing, but it has a big impact on performance and stability.
You got it. It really shows how carefully Adam is designed, that even these little details matter so much for how well it works.
Okay, so we've seen that Adam is a really powerful algorithm. It's adaptable, efficient, robust, and it even handles those tricky situations like sparse gradients and non-stationary objectives really well. But this paper goes even further. They introduce AdaMax. What's the story there?
Yeah, so AdaMax is like a spin-off of Adam. Adam scales the gradients in a certain way. It uses what's called the L2 norm. AdaMax uses something called the infinity norm instead.
The infinity norm. Can we make that a bit more intuitive?
Of course, imagine like focusing on the absolute biggest gradient value instead of the overall size. And surprisingly, this actually leads to a simpler update rule. It might be more stable too.
So it's like we're being extra careful not to get thrown off course by a single really big gradient value. Kind of like saying, hey, let's look at the bigger picture, not overreact to any one thing.
Exactly. It's all about balance, responsiveness, and stability. Now, there's another interesting idea they talk about in the paper, and it's about how we average the parameters over time to make sure our model does well on new data, not just the data we use to train it.
You mean making sure our model can handle new situations, not just memorize the examples it's already seen.
Exactly. So traditionally, we use something called Polyak-Ruppert averaging, which basically just takes a simple average of all the parameters we've seen during training. But this paper suggests that maybe an exponential moving average might be even better.
An exponential moving average.
Yeah.
So that means giving more weight to the recent parameter values.
Yeah, exactly. It's like saying the newest information is the most valuable, so let's give it more weight when we're averaging.
This is making me think about how optimization is not just about finding the lowest point, but also about ending up in a good spot where our model can generalize well. It's like we're not just trying to reach the bottom of the valley, but we also want to make sure we're on solid ground.
That's a great way to put it. And this paper highlights how many things are involved in doing that right. Momentum, adaptivity, bias correction, and even how we average the parameters.
Wow. It seems like the authors of this paper thought of everything. But we've talked about a lot already. Should we pause here and pick up the rest of the discussion in the next part?
That sounds like a good plan. We can give our listeners a chance to process all this and come back ready for more.
Great idea. We'll be back soon to dive even deeper into these fascinating concepts.
Welcome back. Ready to keep exploring Adam and its impact on machine learning?
Definitely. We were just discussing how Adam considers how well our models do on new data, not just the data it was trained on.
Right. And remember how we talked about averaging parameters? The paper looks at an alternative to the usual method, Polyak-Ruppert averaging. They suggest using an exponential moving average instead.
Okay, remind me. What's so special about an exponential moving average again?
Well, instead of treating all the parameter values the same, an exponential moving average gives more weight to the more recent ones. It's basically saying the most recent info is probably more valuable, so let's give it more importance when we're averaging.
Ah, okay. It's like we're focusing on the latest information as we navigate that optimization landscape. But how did the authors actually test Adam and compare it to other algorithms?
They ran a bunch of experiments on different machine learning models and different data sets. And the results were pretty amazing, especially when it comes to how fast they could train models.
I bet. We've already seen how Adam's faster than other methods for things like logistic regression and multilayer neural networks.
Right. But let's dig into those results a bit more. For example, when they trained multilayer neural networks using dropout, Adam was way faster than this other algorithm called the sum of functions optimizer, or SFO.
So even with the randomness of dropout, Adam was still faster.
Yep. It just shows how robust Adam is and how well it handles noise. And this speed up isn't just some technical detail. It actually matters a lot for real-world applications.
Oh, yeah. Tell me more about the practical impact of being faster.
Well, faster training means researchers and engineers can try out more complex models, use bigger data sets, and in the end, develop better machine learning applications. It's like Adam is opening up new possibilities for what we can do with machine learning.
So Adam is pushing the limits in areas like image recognition and natural language processing.
Exactly. And the paper doesn't just show that Adam is fast, it shows how well it handles different kinds of optimization challenges too.
Like what?
Well, remember we talked about sparse gradients and non-stationary objectives? Adam is really good at both of those.
Okay, yeah. Sparse gradients are like when we have lots of zeros in our gradient values, right?
Exactly. And this happens a lot when we're working with data that has a lot of missing or irrelevant features. Adam is good at adapting the learning rate for each parameter, so it's especially well suited for these sparse gradients.
So it's like Adam is saying, let's just focus on the parameters that really matter and not waste time on the ones with zero gradients.
That's right. And for non-stationary objectives, remember our shifting landscape analogy. Adam's use of momentum and those adaptive learning rates helps it navigate all those changes.
So Adam is constantly adjusting course, even when things are changing all the time. It's amazing how it can handle so many different things. But before we go too far, praising Adam, are there any downsides or limitations we should know about?
That's a good question. Atom is great, but it's not perfect. There are some things to keep in mind.
Okay. What are some potential problems?
Well, first, Atom can be a little sensitive to how you set its hyperparameters. These are like the knobs and dials that control how Atom works. And figuring out the best values for these hyperparameters can take a little trial and error.
So it's not always just set it and forget it.
Right. You might need to tweak some settings. Another thing is that Atom isn't always the absolute fastest algorithm out there. For some specific problems, other algorithms might be a bit faster.
So it's not always the speed champion. There might be some cases where something else is slightly better.
Exactly. But even then, Atom is often a strong contender, and it's so versatile. That makes it a good default choice for many machine learning tasks.
It's like the workhorse of optimization algorithms. It might not always be the fastest, but it always does a good job.
I like that. One last thing is that we're still figuring out exactly why Atom works so well, and when it might not be the best choice. Research is ongoing to really understand it better.
So we're still learning more about this optimization superhero. There's always more to discover.
For sure, but even with those things in mind, Atom is a huge accomplishment in machine learning. It's really helped us train complex models and solve real problems.
It's a game changer for sure. And this paper gives us a really good foundation for understanding Atom and how powerful it is. Should we wrap up this part and finish the discussion in our final segment?
That sounds great. Looking forward to sharing some last thoughts and takeaways in the next part.
Me too. We'll be back soon to tie it all together and give our listeners something to think about. Welcome back to our deep dive into Atom. We've talked about a lot, from gradient descent to how Atom works and how well it does on different tasks.
It's been a great discussion. We've seen how Atom takes the best parts of other optimization algorithms, like AdaGrad and RMSProp, to make a more efficient and robust approach.
Exactly. And we've explored how it handles things like sparse gradients and non-stationary objectives, and even the randomness that comes from using mini-batches for training. Plus, we went into bias correction and using an exponential moving average.
Yeah, and we also talked about some of the things to watch out for with Atom, like how it can be a little finicky with the hyperparameters, and that it's not always the absolute fastest.
Right. It's not perfect,
Yeah.
but it's a powerful tool. But now I'm wondering, what about someone who wants to actually use Atom for their own machine learning projects? Where do they start?
That's a great question. The good news is the authors give us some great advice. They suggest starting with the default hyperparameters. They found these worked well for most things.
So we don't have to spend hours tweaking all those settings.
Not right away. You might need to adjust them a little bit, but the defaults are a good place to start. It's like having a recipe that you can change a little depending on what you like.
I like that. That makes Atom seem a lot less scary. It's not this super complicated thing. It's something we can use and adapt to our needs.
Exactly. And you can find Atom in all the popular machine learning libraries, so it's easy to add it to your projects.
That's great. It seems like Atom has made it so much easier for everyone to use really good optimization in machine learning.
I think that's a perfect way to put it. It's given researchers and everyone else the power to do so much more with machine learning.
I agree. But before we finish this deep dive, I want to leave our listeners with one last thought. Something to think about as they continue on their own machine learning journeys.
Sounds good. What wisdom do you have to share?
Well, we've seen how Atom balances all these different things. Momentum, adaptivity, bias correction. They all play an important role. But what if we step back a bit and look beyond the individual pieces? What if the real key to good optimization is understanding how all these things work together and affect each other?
That's a really interesting point. It's like instead of just listening to the individual instruments in an orchestra, we're appreciating the whole symphony.
Exactly. I want everyone listening to think about that a bit more. Explore how those forces interact. Momentum, adaptivity, bias correction, and see what new things you discover.
That's a great challenge for our listeners. It reminds us that learning never really stops.
And on that note, I think we've come to the end of our deep dive into Atom. Hopefully you've all learned something new about this incredible algorithm, its benefits, its limitations, and how it's changed machine learning.
And remember, the best way to really understand Atom is to use it. So go out there and experiment, see what you can achieve with this amazing tool.
Keep exploring, keep asking questions, and keep learning.